Hey everyone. So today we're going to do a problem where we're going to try and find the lowest common ancestor of any two arbitrary nodes in a binary tree. So let's go ahead and look at this example that we have here and make sure that we understand how to do the problem. So we have, for an example here, is 4 and 3. So this node and this node. And when we say we want to find the lowest common ancestor, that's going to be the first node that we come to going up the tree that has both of our nodes that we're searching for as children. So in this case, 1 is the lowest common ancestor because 3 is its child on the left-hand side, and 4 is its child on the right-hand side. And you can also see here with 6 and 7 that 3 is the lowest common ancestor because they're both connected directly to 3, and 1 is also a common ancestor, but it's not the lowest common ancestor because 3 is the lowest common ancestor. So let's dive right into this problem, and the first thing we always want to do is ask any questions we might have of our interviewer. So we just talked briefly about what lowest common ancestor means, but if you come into the interview and they ask you to do this, and you are at all unclear on what they're asking you to do, what they mean by lowest common ancestor, there could be multiple potential lowest common ancestors depending on, maybe not in this case with a tree, but if you were doing this with a graph, for example. There are lots of different things that you might want to clarify with your interviewer, so it's good to just look at the problem and see if there's anything that you're confused about. And another thing that is a good question to ask here, and you can tell from the example that this is not the case in our example, but it could be the case in general, is whether or not this is a binary search tree. And so obviously the difference between a binary tree and a binary search tree is that the binary search tree is going to be sorted. And that's going to make it actually pretty easy to solve this problem because, for example, if we had a tree where 3 was at the top and then we know that our nodes that we were looking for were, or let's say we had the parent node was 5 and we were looking for 1 and 3, the lowest common ancestor of 1 and 3, then we know that those all have to be on the left branch of that tree. And they may be further down, but it's very easy for us to sort of narrow in on where our two nodes are. And when you look at a node, you can immediately tell whether or not the two nodes that you're looking, whether if you look at a given node. So let's say we look at this parent node, and then you can easily tell whether the two children that you're searching for are on the same subtree or different subtrees. So we could actually solve that problem in log n time because you only have to look at each parent node to determine, especially if you already know that the two nodes are in the tree. So because it gets a little more complicated if you don't know for certain that the two nodes you're searching for are actually in the tree. So let's go ahead and talk about how we might solve this problem. And there are a couple options. The first, obviously, is if it is a binary search tree, we can do something with looking at the actual values. But that's not really relevant here. So the first thing that comes to mind for me is that what if we were to do this recursively? So for example, I could easily say, is a given node in the right subtree or the left subtree? And that would be a fairly simple problem for me to solve, right? Because you can just do a depth first search, a recursive search down through the nodes of the tree. So for example, I could say, is 5 in the left subtree or the right subtree? And so I would traverse down here, I don't find it, but I come to here and I do find it, and I would return back up to the top. And that would be fine. And what I could do is, as is probably apparent from going through the example, we know that if the two children are on different subtrees of our parent node, then by definition that's the lowest common ancestor. Because we know that if a node is on this right subtree, then it's the only way that it's connected to any node on the left subtree is through this parent 1 node. And so we could just say, for example, recurse through our tree and say, are the two nodes that we're searching for on different subtrees? Is one on the left and one on the right? And if they are, then we know that we found the right answer. And if not, then we would have to go through and go down a level and search again. And we could do this, but it's not going to be very efficient, right? Because we're going to end up searching through all the subtrees and all the nodes multiple times. So we would have to come up with some way to optimize this where we would basically find the point at which the two subtrees diverge while we're doing the traversal, so that we're not traversing the whole tree many times. And I was actually thinking about this originally when I was solving this problem. I thought that seemed like it was going to be a good solution, but it's actually not. It gets pretty complicated because you need to either do something fancy with your return values so that you know whether the node's on the right subtree or the left subtree, and it gets a little tricky, and it's just not really necessary. It doesn't give you any real benefits in terms of efficiency. So I'm going to take another approach that I think is slightly simpler. And let's think about if you were to just take the path from one node, from the root to each node, then you could see where those paths diverge, right? So let's look at this example of 6 and 7 again. We get the path to 6 is 1, 3, 6, and the path to 7 is 1, 3, 7. And so we could just go and say, okay, the 1s are the same, the 3s are the same. So at what point do we get to do the nodes diverge? And at that point, we know that when they're no longer the same, it means that the path is split, and so now we have on 2 separate subtrees. And so what I'm going to do is I'm just going to find the path to each node, and then I'm going to go and compare the paths. And by comparing the paths, I can see where the paths diverge. So that hopefully makes sense, and that's going to be a reasonably efficient algorithm, because by finding the path is just going to take O of n time, and then comparing them is going to take O of log n time, because that's going to be, if we assume, a relatively balanced tree. So let's go ahead and actually code this up. And the first thing we need is obviously a private node class. And this is just going to represent our tree. So we're going to have a private node left and private node right. And you might want to have a value for this node. In this case, we're not actually going to use the values at all, so I'm just not worrying about it, but you could ask your interviewer what they'd prefer you to do. And then the first thing I'm going to do is write this function that is going to find the path to a given node from the root of the tree. So I'm going to call it public, and it's going to return a stack, and the stack is going to be the path. So stack of nodes, and it's going to be path to node tree and node n. And in this case, I chose to use a stack because I think that a stack, or you could potentially use a queue too, it just would end up having the reverse order, and so you'd have to flip everything around a little bit. But I think one of these data structures can be super useful, especially when we get to the end, when we're actually trying to compare them, because all we're going to have to do is keep popping items out until one of them is empty. And if one of them is empty and we don't find any nodes that differ, then we know that one node is the parent of the lowest common ancestor. So for example, we'll have, let's say that we were comparing 3 and 7. We would get the stack 1, 3, and we would get the stack 1, 3, 7. And so we'd pop 1 from each stack, and then we'd pop 3 from each stack, and now the one stack is empty and the other stack has one number left, so we know that now 3 is our value. And that's going to just make it pretty easy to do it that way. And it also sort of makes sense for when we're actually generating the stack, because we're going to go down, we're going to recurse down all the way to the bottom. We're basically going to recurse through until we find our target node, until we find the node that we're searching for. And then as we recurse back up, we're just going to push items onto the stack, and we're going to go all the way back up to the top. So that's going to be fairly straightforward for us to do. And we're going to do this recursively because it's a tree, and that makes sense in this case. So what is going to be our base case? In this case, we have sort of 2 base cases. The one is going to be if tree is equal to null, then we know that we've searched through this branch of the tree and we've not found our target node. And so in that case, we want to return null, because that's going to be our way of signaling that we didn't find what we were looking for. So we're just going to return null. And if the other base case is going to be if we find the node that we're looking for. So we're going to say if tree.equals n. And I should put in a quick aside here. We're not going to explicitly implement an equals class here, or an equals method for node, because I'm going to assume that we're actually using the same objects. So we're going to be comparing object references, and that's going to be good enough in this case, because I'm going to say that like you're not going to basically have a duplicate of the same node. So we're not comparing them by value or by something else. I'm going to assume that we're actually looking at this, we're searching for the exact same node object. But this is a conversation that's worth having with your interviewer to let them know that you're thinking about, these are important things to be concerned about when you're actually writing production level code. So it's a good thing to think about. But in this case, it's going to be fine the way it is. And I'm going to, if it's equal, I want to create a new stack and then push the node onto the stack. And then that's going to be the stack that I'm going to return up and push items onto as we go up the stack. So all we have to do is just create a new stack. I'll do stack of nodes, and I'm just going to call it S, and it's going to be a new stack node. And then I'm just going to push on n, or I'm going to push on tree or n. It actually doesn't matter because they're equal in this case, right? And then I'm going to return stack. So I'm going to do s.push tree and return s. Okay, so those are our two base cases, and now we need to look at the other possibilities. So what I'm going to do is I'm going to recursively call this on both subtrees. And then I'm going to assume that in this case, especially since we're looking at the specific node objects, each node is going to be unique in the tree. We're not going to have the same node, or I'm going to assume that we're not going to have the same node more than once in the tree. And that's actually something that you should check with your interviewer, because that wouldn't really make sense, because depending on how you're treating it, that would basically lead to there being a loop in the tree, which doesn't make sense. But it's good to clarify anyway that each node is only going to occur once, so we're not going to have to worry about there being a duplicate of the same node. And the result is going to be that I'm going to call this on the two subtrees, and then one of those is guaranteed to be null, right? Because we're going to get to here and we're not going to find the node that we're looking for, and so that's going to be null. And then the other one may be null or it may not be null. And so if the other one is null, then I know that I didn't find the node that I'm looking for at all. And if the other one is non-null, then I'm going to take that stack that gets returned, push on the current value, and return it up the stack. So those are going to be basically our two options here. And so I'll just say that the stack, I'm going to call it stack left, and that's going to just be path to tree.left and n. And then I'm going to do stack node right. Right, and then that's going to be the same thing, but with the right subtree. So path to tree.right and n. And so now that we have those two stacks, we're going to say if left is not null, so only one of them can possibly not be non-null in this case. So we're just going to deal with each case separately. So if left is not null, then we're going to say left.push tree, because we want to push our current node onto it, and then return left. And if right is not equal to null, then we're going to do the same thing with right. So we're going to say that in this case we do right.push tree and return right. So that's going to be the two cases where we find it, and otherwise the one remaining case is if we don't find it, and then we're just going to return null, because again, that's our sort of cue to ourselves that we didn't find the node. And so hopefully this makes sense. This should be fairly straightforward, although the recursion does make it a little bit trickier. And now let's go ahead and I'm going to implement our actual function that's going to find the lowest common ancestor. So I'm going to just call it, I'm going to say node, and then it's going to be lowest common ancestor. And it's going to take in a node tree, a node n1, and a node n2. Just like that. And so we're first going to say we can do a couple checks right out of the way. So first of all, if they're the same node, if we get passed in the same node, then it's its own lowest common ancestor, right? So that's going to be really simple, and we can just do if n1 dot equals n2, then we just return n1 or n2. And otherwise, we're going to get the two paths, and then we're going to compare them like we were talking about. So otherwise, we're going to say stack path to n1 is going to be path 2, tree, and n1, and stack path to n2 is going to be equal to path 2 and tree and n2. Then we're going to say that if they're both null, we can return null, because if they're both null, then, or sorry, if either of them is null, then it means that the node is not, that it means that one of those nodes is not in the tree. And that's going to mean that neither of them, that they're not going to share any ancestors. And so if either of them is null, we can just return null. So if path to n1 equals null, or path to n2 equals null, then return null. And otherwise, we are going to go through and we're going to compare them. So I'm just going to create a node that's going to track sort of the current ancestor. And so node prev is going to be equal to null. And this is, we know that, so what I'm going to do is I'm going to go through the stacks, popping items off, and then as long as the stacks are not empty, and then adding the, and then setting that item to be prev. And then once I find the part where they diverge, I'm going to return prev. And I know that prev is never going to be null, is never actually going to be null, because I know that the two stacks are both going to be non-empty. Because because I know, because of the way that I wrote path 2, it's always going to have at least one node, which is going to be the result node. It's either going to be null, in which case we dealt with that here, or it's going to have at least one item in it. But the compiler doesn't know that, so the compiler would complain if I just did this and then set it and then return prev. It would say that it could be uninitialized. So we have to set it to null in this case. And then otherwise, I'm going to do while both stacks are not empty. So while not path to n1 is empty, and not path to n2 dot is empty, I'm going to pop off both and compare them. So I'm going to say node s equals path to n1 dot pop, and node t equals path to n2 dot pop. And then I'm going to say that if they're equal, I'm going to set that to be prev, and I'm going to continue. And otherwise, I'm going to break out because I've found the point where they diverge. So s dot equals t. If they're equal, then I'm going to say prev equals s, and otherwise I'm going to break. And finally, I just have to return prev. So that's our code. It's a little bit long, actually. This is one of the longer problems we've done thus far in terms of amount of code. But let's go ahead and actually see that this works the way we expect it to. So I'm just going to go through one example because it's going to take a little bit of time to go through the examples, and you can go through and should go through more examples on your own. And particularly, I don't usually do this in these videos because I don't usually have time to, but it's good to think about what are potential corner cases, or what are potential cases that could cause errors in your code. And it's good to explicitly test those cases, especially if you have time to do it, because it shows that you're thinking about all the different possibilities rather than just, oh, here's the ideal case in which, like, yes, my code works correctly in this case. But that would be like, for example, testing a binary search where your array length is always even, for example. Like, doing these things, you want to make sure that you're handling these different cases. So let's go ahead, and I'm going to use this tree, and I'm going to test, let's say, this 4 and 3 here. So let's come down. We're going to call this here. We're going to call tree is 1, node 1 is 4, and node 2 is 3. So they're not equal to each other, and then we're going to get the path to 4, and the path of 3. So let's copy this down again. And we're going to first get the path of 4. So path to 1 and 4. And let's see. So the tree is not null. The tree is not equal to 4. So we're going to come down here and we're going to get the left path. We're going to go left first. And so we're going to say left is going to be, we're going to say tree left. So path to 2 and 4. And then we're going to do the same thing again. It's not null and they're not equal. So we're going to come down here and we're going to call path to 4 and 4. So now they're equal, and so we're going to create a new stack, and we're going to push tree onto the stack, which is 4. So now we have our stack is going to be equal to, so stack is equal to 4. And we're now back here. We're going to go to the right path. It's going to end up calling it again, and it's going to be null. So it's going to, I'm not going to go through all the details, but it's a little hard. It's especially hard to sort of type this out, but you can definitely draw it out on the whiteboard, and this would be good to go through in a little more depth than I'm going to go through here. But we're going to return null, and so we're going to say that left is not equal to null, so we're going to push left, we're going to push tree, which is 2, and then we're going to pop up again, and again we're going to get that the left is null, so we're going to push 1. And that's going to be our, so now that was our path to N1. And then we're going to do path to N2, which is going to be much the same. We're going to first go through the entire left subtree is going to return null. And then we're going to go through the right subtree, and we're going to get that they're equal. So we're going to push 3. So we're going to get that, in this case, stack equals 3. And then we're going to return 1, and we're going to add stack equals 1. So that was a very, very quick going through of that code, but hopefully you get the idea, and you could go through it more on your own time. And these are our 2 stacks. So this is path to N1, and this is path to N2. So now what we want to do is we're going to come down here. Neither of them is null, and so prev equals null. And so we're going to say that S equals 1, T equals 1, and they're equal. So we're going to set prev is equal to 1. And then we're going to continue, and now we're going to say S equals 2 and T equals 3. And now they're no longer equal, so we're going to return prev, which is equal to 1. And that's what we expect. So hopefully that made sense. That's a quick overview of running through the code. And I guess the last thing that we want to think about here is what is going to be the runtime of this code. And I already mentioned this briefly earlier, but the way that I usually think about this is let's break it down by parts. So the first part, or by function, especially since we have multiple functions here. So path 2 is going to take O of n time. And the reason for that is, like with many of these things where we traverse the tree, we're going to traverse all the up to every node once, right? So we're going to go through most of the nodes in the tree, but we're not going through nodes multiple times. We're not going to be hitting the same node repeatedly. We're going to go through each different node, and then we're going to create this stack and push onto the stack, but that's not going to affect us because that's only going to be they're going to be like O of log n pushes onto the stack because it's the height of the tree, right? So we're basically just we're traversing every node in the tree once. So that's going to be big O of n. And then we can take this and come up and look at our lowest common ancestor method. So we already have O of n for this path of tree, and we call that twice. And then we're going to do this, and this potentially could take O of n time as well. The average time in this case, if we assume we have a balanced tree, this is going to take O of log n time, right? Because it's going to be the height of the tree. But if we don't assume anything, and we assume that it could be a tree where all the nodes are in a line, then potentially the depth of the tree could be O of n. So this is also going to take O of n, which is added to our existing O of n. And so we get that the time complexity, when you sum those together, is going to be O of 2n or O of n. And we can also look at the space complexity, which is a little trickier in this case because we have this recursion. But if we look at this, so again, this is going to depend on whether we have a balanced tree or not. And so let's think about both cases because they're both interesting cases. So let's assume first of all that we have a balanced tree. And since we're doing recursion, we're going to have to store the whole recursive stack. And then we also have this stack that we're generating. And so if it's a balanced tree, then we know that our recursive stack can only ever be O of log n deep, because we're only going down. We're never doing, we're not doing like multiple recursions at the same time. You're always following one path through the tree. So if we go back and look at this tree, we're going to store this. We're going to come down here, store this, and then we're going to come down here and store this in our recursive stack. But then before we come over to this next one, we're going to pop the 4, so we're no longer going to have to store that part of the recursive stack. So our recursive stack is always going to be maximum of the depth of the tree. And so if we consider the good case, then that is O of log n. And if we consider, if we consider the balanced case, it's O of log n. And if we consider an arbitrary case, that's going to be O of n. And the same is true for our stack that we're creating, right? Because the stack is also could be up to the depth of the tree. So our space complexity here for our unfortunate case where it's not balanced, which is what we have to assume here, is going to be O of n. And then again, we will go up here and look at this, and this only takes up a constant amount of space, right? Because we're going to generate 2 stacks. Well, it takes up a O of n space because we're going to generate 2 stacks the same way that we have, and that's going to take obviously the same space as it did in the other function. And then we're not using any additional space. So in this case, our space complexity is also going to be O of n. And hopefully that made sense. It's a slightly involved problem, but I think it's a useful problem, and it's a pretty popular sort of problem. So hopefully that made sense. If you have any questions for me, let me know in the comments below or on the blog, and I will see you guys again next week.